Hi, welcome back. So in chapter 3, you must know the outline matrix, eigenvalue, and eigenvector. In this outline, we're going to expand the toolkit that we have so far learned on what we must know in order to make a good prediction or in order to master the skill of doing good analysis by understanding the concept on the use of matrix as a representation of solution. Now, when it comes to the eigenvalue and eigenvectors, they are actually a title or a specific topic on the study of matrix and linear algebra anyway. If I would have to represent 2 points here, I've come now to appreciate the meaning of graphing this in certain axes in 2 dimensions just for a simple presentation in this case. Maybe if I would have to draw a line like that, it turns out to be a shape that we're familiar with. I just transferred an object, a real life, into some kind of mathematical shape in a geometry perspective, right? I could from here, define a kind of origin at this point, maybe a point here and a point here, since I can capture it by x and y, and I can represent kind of angle. It could have another shape. All these way of presentation and visualization are important things. One of the problems, as I said, the area maybe can be at interest, maybe the distance between these points can be at interest, can be a path, can be calculation for a certain length. I hope now you could remember some of the basic ideas in the trigonometry. Now we're going to actually bring a whole new concept which we call a vector. What does a vector presentation means? Well, vector usually are the practice of writing vector. You could choose a letter, for example, it could be U, 2 opening brackets separated by comma, depends on the dimension. So you got dimension 1, 2, 3. To define this arrow, we need to give it a kind of a magnitude. This is the magnitude. I assume the first entry here is going to represent the X movement, and it's going to present the Y movement. How about if I subtract them from each other, the movement of the X and the movement of the Y, just like what I did with the distance things here. Here is where we need to understand the vector represent the magnitude, that's one property of it, and represent the direction. Having to draw this line this way, completely different having to draw the exact same line this way. So in this case, I'm going to say, well, 1 minus 0 is going to be 1 here, and then 2 minus 0 is going to be 2 here. From the origin all the way up, pointing toward this direction. So I get a magnitude and I get a direction. Now, this presentation turns out to be quite a bit important. Well, I can represent the other vector exactly the same line. I could now connect these 2 points as well by drawing another vector. Well, the direction of this vector is another issue to discuss. Well, shall I go this direction or shall I come to this direction? And this is where you're going to utilize the idea of operation of vector, and that is the property of addition and the property of scaling. Now, it turns out if you want to add u vector to v vector, and then the new vector or the addition of u and v, which we call it equal to k, is going to be actually this from the origin to this new vector here. And that leads me to the idea of what's called the length, which is called the norm anyway. Square root of the first entry plus y0 square, and this scalar represent a length of this vector. The second thing I'd like to talk about, it's scaling a vector. Scaling a vector means to scale v by a certain quantity. If I take this u and I scale it by a certain value, by a number, like say 2, means take the length of that u and it's going to be twice as long. Now let's go ahead actually and see some real implementation. We get this point and this point, I could easily draw a vector from the origin to point B and a vector from the origin to point C. So I get these 2 vectors now, have to kind of draw this point down here, and then the new vector, which is going to be again from the origin, is going to be this point, u plus v. How about if we just go into scale u twice as long? Now it did not change direction, it's still in the same direction, just expand the length twice as long. Now I have a new value called a vector. Let's scale v, maybe half. I get a new vector called b. Now again, I can just go and add a plus b. Is going to be the point in here. How about if I would like to subtract what is the vector u minus v? U minus v or v minus u Is it going to be different? Well, yes, it is going to be different because this direction here, this vector represent u minus v. But if I draw this direction of a vector, it's going to be v minus u. See the directionality. So when we come back to our example, if I say, well, u minus v, this kind of direction, it's going to have a negative in terms of the x, positive value for the y's. What we got here, as we expected, we got minus 2 and we got 2. We could take the exact same idea with the 3 dimension. I think next maybe we can see some property around vectors, maybe some practical problems that really where you can utilize vectors anyway, and then derived from the idea of the law of cosine when we have a kind of acute angle just like this theta here. Of course, if it is normal angle, this term entirely will be gone, and then you will left only with c squared is equal a squared plus b squared anyway. Now, what I would like to do, I would like to expand the idea from here using the concept of a vector. I think, for example, this is going to be like, say, the length of the A, and this is maybe we can take the length of this side of B, and vector C, which we have in here. Either way, we can like go that direction, or we could go in that direction. So either way, I mean, you may think about it. And what I can do, I can substitute from this equation. I could actually write this as b minus a squared into this form here. So let me put down my essential equation here. Now, if I do some algebraic transformation, this, what you see here, is called the dot product theorem. So basically, dot product, it says that if I would have a vector A and you got a vector B, A dot B, I mean the dot product exactly equal B dot A. So either way, and it's going to be a scalar value. But at the same time, I would like you to know that also the dot product, I mean, considering if you have brought a factor of the angle between them, then you're going to lean into this particular equation by capturing the length of the A, length of the B, and then you have to have the cosine theta, or the angle between them, and you can apply this function here. Now, I would like to speak also about some special kind of vector. If you take the original vector A divided by its length, that kind of vector, we call it a normalized vector, a scalar vector, or you can call it a unit vector. If you want to project A on B, it means like to find out the shadow of A on B. Projection A on B is written in many books as comp A project on B vector. The idea start actually by basic trigonometry again. I could actually represent this adjacent in terms of the hypotenuse and in terms of the theta. Look at this case, this A is going to be sort of my hypotenuse, and this is going to be my theta, right? And this is going to be my adjacent, the vector I am interested in. I could say easily that the projection of A on B is just equal to A vector multiplied by the cosine of theta. But if you get back to the previous section here, we have seen that the actual cosine of theta can be written in form of vector of A and B as a dot product. So if I want to substitute the value of cosine of theta, well, this is a very nice and handy thing to do, because basically what I can do, I can get rid of this. But we have a small problem, and I hope that you can capture it. You see that we have this long path of B. I am not interested with the entire vector of B. Actually, I am interested only with the unit that represent the direction and the magnitude of this particular vector B. And if you remember the special case of a unit vector by taking a vector and divided by its length, that will give you a unit vector. So if I take this entire term multiplied by B divided by its length, I will be finishing up with the entire application on a projection A on B. Practical idea of that. Imagine if we would like to capture the distance between this point and this line, and the shortest distance, according to our understanding from Pythagorean theorem, project from this point a line on this function with a right angle, then you are actually measuring the shortest distance. Well, first of all, I get origin here from this point, for example. I could just drag a line here to this point, and the vector A is easy to capture. That is this point minus the origin of 0 and 0. We want this particular point. And how can we get to that point? First of all, let's convert this line, function equation, into a kind of a vector. We can see the slope of this line. It is 2 units of y over 1 unit of x. So we got two vectors. Let's try to make the application of our equation here. Now this vector 3 of 6 represents the projection of a on b, which is actually this vector here. This can be a point actually, since we have the origin is 0 and 0. It's easy to see that we have now a point which is 3 and 6. We have the origin point 5 and 5, and I can easily find the distance between them. So square root of 5 represent the distance between this point and this line. Let me get back to the idea of this vector here plus this vector here. As we said before, it's going to form this parallelogram, right? What is the area of this one? First of all, you see the diagonal of this parallelogram represent the sum of the two vector u and v, and it represents half the triangle of this parallelogram. But if I want to find the area of this parallelogram, well, using the basic geometrical fact that we've learned, first of all, we know there's going to be the base multiplied by the height. Line here represent the height as 3.2, this point here 5, so I get a base equal 5, that is equal to 16. So 16 is the area. Let's see how can we actually do that using a vector. Now don't forget the essential vector that we have, the vector u and vector v, 2 and 4, 5 and 2. What basically I want to show you now is how to form a matrix from this. Now, what is matrix in general? Now, matrix basically represent columns by number of rows. You have to look at the column as representing a dimension or a variable or axes. In this case, we got x and y. So this is one, this is x and this is y. The row, on the other hand, represent the changes of these points. So basically, if I look at this, where this represent the change of the x dimension and this is the y dimension, and this matrix seems to be 2 by 2 matrix. It could also be represented as 2 and 5, right? And I could look at the y vector, which is this guy here. It could represent a 4 and 2. I don't want you to be actually misled because many material maybe they fail to explain the idea in here. So yes, this is a vector that started from the origin to some point, but don't forget the vector, the element of that vector represented, or the way we represent this vector in terms of the changes on 2 dimensions, right? So it turns out that you can capture something called the determinant of A. And what does the determinant of A of 2 by 2 matrix is a simple calculation by taking the diagonal multiplication minus the upper diagonal. That will lead you to the value of minus 16. And as it turns out that the absolute value of this determinant, the absolute value of 16 is going to be 16. It is actually the area of the parallelogram that these two vectors has formed. Now, the determinant of 2 by 2 matrix is quite easy to do because the formula is just straightforward. However, if this dimension grow a little bit, let's say now if I would have a 3-dimension vector, determinant cannot be calculated for non-square matrix. We need to be a square. So this isn't a square because it's going to be 2 by 3, right? 2 by 3, which is not square. So we need to square this matrix. That's why we add actually something called an entry of I, j, and k. And the basic idea to capture the determinant of this A matrix, taking the entry of I, which is this guy, and then you cover the row of it and the column of it, and then you got the determinant multiplied by the determinant of this 2 by 2 matrix. This is the first thing you need to know. And then next thing you also have to know that the entry here is going to be positive, negative, positive. Imagine the sign of each of these entries. So minus j multiply again by the determinant of this 2 by 2. Finally, plus k multiply again by the determinant of this last side. The purpose of this actually to introduce you to a concept which we call it the cross product. The cross product will introduce you to another vector we call C vector. One thing you have to know that A cross B, it isn't equal to B cross A. So let me show you a real example of a 3-dimension. So we got this triangle from these 3 points in the space. I'm not connecting from the origin of A. If I ask you, what is the area Now the cross product of two vector u and this vector v, is captured or calculated same formula as we did in here. The idea here, I want you to know that the cross product between two vector, it is a vector. So let me go actually and draw this vector, show you what it looks like. Now what is special about this vector? It turns out to be perpendicular in both vector in the space. If you want to confirm that, you take something called the dot product between them. So 4 times 0, it is 0, plus 0 times 1, it is 0, plus 1 times 0, it is 0. The dot product between two vector is 0. That means the two vectors are perpendicular on one another. Don't forget that we know that a dot b, it is the length of the a by the length of the b by the cosine theta between them, and cosine theta of this, it is 0, so this entire term will be 0. So to know the direction, it depends if you take a cross b or you take b cross a, the direction will be different. And it turns out that the length of this w, it is equal to the area of this parallelogram that a and b has formed together. So if I calculate the length of this, I will capture the area of this parallelogram, and half of it will be equal to the area of the essential question that I ask you: what is the area of this triangle? So this is the area of the triangle. But I'm going to show you a case. We call it two vectors. One of them is the base of the other. So it turns out that u, it is just scaled by 2 of the vector v. To this end, we call vector v is the base, and u, it is linearly dependent or expanded by scaling the vector v actually. Now we reach to one important application, since we have understood matrix, vector, etc., is to understand the meaning of eigenvalue and eigenvectors. That's exactly what we're going to do next. I will see you then.